left off here. So yesterday we had kind of talked about how to go in between logarithmic and exponential form and kind of how to solve logarithmic equations. Now we're going to get into the graphing side of things. So I want you guys to think back, because we would have done this in section 1 when we were graphing an exponential function. So something like f of x equals this 3x. I'm just going to highlight this. Okay, so I'm talking about this equation here. Whoop. If I can get it to highlight, there we go. F of x equals 3 to the x power. When we were raising our numbers, like we used our table for this, right? We were taking 3 and we would raise it to all kinds of different numbers. Like we usually set up our table so that it was between -2 and +2. So let's go ahead, grab our calculators here, and we can still type this in. So you can hit 3 and you can raise that to the x power. And then you can go to your table, you can start it at -2 and whatever, and you're going to start to get some numbers, okay? Now I have mine written as a fraction here, but you guys might have decimals, and that's okay. So 3 to the -2 power would be the same thing as 1/9. Now if I had 3 to the -1 power, that would be the same thing as 1/3, or you might say like 0.3333 repeating, okay? 3 to the 0 power would be 1. 3 to the first would be a 3, and 3 squared would be a 9, okay? So those were all of our numbers that we would have seen from our table, and then we would have graphed these points, okay? So I'm going to come over here, I'm going to graph this first one in green onto my graph here. I'm just going to zoom in for the graphing part. Okay, and then we're going to connect this here. All right, and so that's what it should look like. And we saw graphs like this in the past, and we talked about how the domain would be -infinity to +infinity, because we could put in any x value that we wanted to. But then we talked about how this graph is never going to cross the y-axis, the x-axis. It's never going to approach or equal 0. So my asymptote would be y equals 0, and my range would be 0 to +infinity, okay? It's going to continue to get as close to 0 as possible, but it's never going to actually equal 0. Now let's think about how we would graph this if we're doing it logarithmic, okay? And we saw yesterday about how we can go back and forth between log form and exponential form. The logarithmic function, like if you had something written as a logarithmic function here, that is actually considered to be the inverse of the exponential equation. And in the past, we've talked about inverses. That's just when you take your x and your y coordinates on your table or on your graph or on the figure that you're working with, and you just flip them, like you just switch the order of the x and the y. So that's what we're going to see happen down here. So if I look at this, like I'm just going to zoom out so you can see this kind of big picture. If I'm looking at this new equation that says g of x equals log 3x, that's still dealing with that same equation that we saw up above, but it's the inverse now, because we took that exponential equation that I had, 3 to the x power, and I rewrote this as a logarithmic equation. I would take everything from up above in my table, and everything would switch its spot. So you can see how they took the 1/9 and they made that become my x, which would mean that my y would become a -2. So this would be, well, let me change my color so it matches. I'm going to do this one in blue. So this would be -2. That means that if I plugged in log base 3 and I did 1/9 in for my x, I would get -2. Okay, and so I would keep doing that for the whole table. The next x value I would do would be 1/3. And so if I plugged in log 3 to the 1/3, that would equal -1. And then if I did a 1, it would be log 3, 1, which would equal 0. Okay, and so I'm just going to kind of keep using that to fill in the rest of my table here. Okay, so you can see all those numbers flip positions here. And now I'm going to go to my graph, and I want you guys to see this, okay? So I'm going to zoom in on my graph again, just because this is a really small grid that I have. But if I were to go 1/9 on my x-axis, that would go to -2. So again, I'm going to have to just guess where I think that is. And then 1/3 would be at -1. 1 is at 0. 2, or I mean 3 is my next point, is up at 1. And then 9 is at 2. Okay, and then I'm just going to graph this. So I also hope you can see how we basically took that green equation, my exponential function that I graphed first, and I'm reflecting it over the line at y equals x, which would be this line right here that kind of goes through the origin and has a slope of 1/1. But all of those points got flipped over that red dotted line that I just drew in there. And that's always what happens with our exponential. I'm sorry, I meant to say that that's what always happens with our inverses. Anytime that we're doing an inverse graph, it always reflects over that line. Okay, so even when you had just a simple linear equation and you found the inverse, it did the same thing that this is doing right now. Now you can see how this is going to maybe impact our domain and our range a little bit differently. So if we kind of come back down here, they're wanting us to write out what's our domain and our range. Now this time, domain is your x values, and it doesn't look like x is able to go below 0 here. So I would say my domain would be anything at 0 or bigger. So 0 to positive infinity would be my x values that I can use. My ranges, though, now seem to be not affected by any specific number. Like I have some positive y's and negative y's, and it looks like it continues to go in both directions. So my range now is negative infinity to positive infinity. And now this time, because of that domain restriction, that means that my asymptote is going to be at x equals 0 instead of y equals 0. So you can also kind of see how the domain and the range relate to each other between these two. Some things get flipped around, just like they got flipped around on our table. Okay, so I want you guys to practice this. If you guys turn your page over to the next page here, I want you to now practice graphing the exponential 4 to the x power. And then I also want you to do the logarithmic graph of log 4 to the x. So just practice what we just talked about there. And then right underneath that, go ahead and fill out what you think your domain, range, and your asymptotes would be for the exponential and the logarithmic equation. Okay, I'll give you a little bit of time to work through that. All right, if you're still finishing up, that's fine. I'm just going to get started on filling out my kind of tables that I would have used in order to help me graph, okay? Okay, so just take a look at those two. Hopefully you can see all that. I know the graph gets so small here on the screen, but these would have been my tables. I would have just started by finding the table for 4 to the x power. I would have just used my calculator for that. And then for the logarithm table, I just flipped my numbers around. So I didn't even really do the math there. I just used the fact that I know that those should switch around. Okay. And then I graphed them both so you can kind of see that. Now let's fill out what we should have written down here for domain and range and all of that. So for the exponential, the domain should have been negative infinity to positive infinity. Range should have been 0 to positive infinity. And then your asymptotes would have been just y equals 0. And the logarithmic one, the domain and the range, they basically flip-flop. And your asymptote would be x equals 0 instead of y equals 0. All right, any questions on how to graph that? Okay, now we're still going to graph here on this next thing, but we are going to be talking about transformations. And so if you kind of look at my graph that I have, they are already graphing this parent for me. So the red line that's on my graph here is this equation log 3x, which we talked about on the previous page too. Like we found the values of that using our table. So they're just already providing us with that graph. What we can start to see happen though on these is they might do some transformations where they're moving a graph, left, right, up, down. Those kind of movements can still happen even when we're dealing with exponential or logarithmic equations. So with a log form, if the minus or plus number is inside the parentheses with the x, that is going to force it to go either left or right. Now, if it was just a number added on after, no parentheses were involved, then it would move it up or down. Remember, when the number is placed in there and it's moving left or right, we always have to think opposite. So I know it says -2, but really that means they put in a +2, and they're kind of showing you how they get to that. So it means that it's going to go 2 to the right. So all I'm going to do is take these points and I'm going to move it 2 to the right. Now my original asymptote would be on the y-axis here. Okay, so that's the original one for the parent graph. For my new one, my asymptote would move right 2. So this would be like my new boundary point. Okay, and all those points that I had would move right 2 as well. So, I have a point at 0, 1, that's pretty clear. I'm just going to go 1, 2, and it's going to be at 0, 3 instead, or sorry, 3, 0. I spoke that backwards. I also had a point that was at 3, 1, so I'm going to move that 1, 2, so now it's at 5, 1. Okay, and then another point that I can see pretty clearly was at 9, 2. If I move that right 2, it goes here. Oops, I must have changed my color by accident there. So it goes to 11, 2. And then it would continue to go forever in this direction, and it would continue to come this way, but it would approach that new asymptote. Okay, so it's really not super hard to graph a logarithm equation like that using its transformations. You just have to figure out what direction it went in. Okay, so if you guys take a look at this next one here, this is using the log 4. Okay, so I'm looking at this here. This means that your parent graph, I'll just write f of x would be log 4x, and that's the example that you guys had to do on your own. So if you don't remember, we can fill out a little table here. That was the 1/16, the 1/4, the 1, 4, and 16. Those were all of my x values. And then when we plugged it in, we got -2, -1, 0, 1, and 2. So I'm going to go ahead and graph this. Okay, so there's the parent. Now take a look at your new one up here. What is this going to force it to do? What's that +5 going to make it do? Yeah, this time it's going to make all those points move left 5. So on my graph, all these points need to go left 5. Okay, so if I count, even just from my original points, I would go 1, 2, 3, 4, 5. I'm starting on the far right point there. 1, 2, 3, 4, 5. So now we can kind of see our new line here. And you can see also how now that new asymptote would be at that point at -5. So you could draw that in too if you really wanted to see that. Like so. All right, any questions on how to use the transformations there? Okay, so far a lot of the things that we've done as far as like with logarithms, we haven't really exclusively been like typing stuff into our calculators for the logarithm. We've been doing a little bit with the exponentials and then using that to help us get to our logarithm. Sometimes though, we can use our calculators to help us solve certain logarithms. So if you guys go to the next page, we're going to talk about something called a common logarithm. A common logarithm is when it's a base 10. So a lot of times, it could be written with a 10 here, like in the 10 would be in the subscript spot. But what that really means is it would look like this, log x. If something is a logarithm with a base 10, we normally don't keep the 10 in the spot. We usually just kind of drop that from the problem. So if you guys look at your calculator, there is a log button. It should be kind of on the left side, right next to your numbers. You should see a button that says log, okay? And you'll see like when it has the log there, it doesn't give you an option to put in a base number. And that's because when your calculator is doing a logarithm, especially if you just have like a real basic calculator, it's not going to let you customize the base number, okay? It's going to just keep it as log 10. So when we're doing operations with just a common logarithm, so it has a base 10, we can use our calculator to help us do that. Okay, so let's do some examples here, and we're going to have to maybe use our calculator to help us solve this. So this says that the percentage of adult height attained by a boy who is X years old can be modeled by the equation f of x equals 29 plus 48.8 times the log of x plus 1, where x represents the boy's age from 5 to 15, and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has a boy attained at age 10? So x represents, remember, the boy's age. So if he's 10 years old, we're going to be putting 10 in for x. So using my equation up here, I'm going to take 29 plus 48.8 log, and instead of x, I'm going to put 10, and then it's going to be plus 1. So it's going to be just rewritten like that. And then what I'm going to do is use my calculator here. So I'm going to type in 29 plus 48.8. Now I'm going to hit my log button, okay? So it's going to automatically pop in log and then parentheses. And in here you can do 11, or you could type out 10 plus 1 if you really wanted to. Okay, we're going to hit enter, and we're going to round this here 79.8, or if you wanted to round it to a whole number, we would say 80, okay, percent. So 80% of his adult height is going to have been reached by the time he turns 10 years old. Okay, so that kind of gives you an idea of how you would maybe use that logarithm button on your calculator. Now we also have something called a natural logarithm, and this is a little bit different. It doesn't write out log, instead they just use ln for natural logarithm. They just kind of switch the order of the letters. If you guys look at your calculator, the ln button is usually right next to the log button. So sometimes they're separated, like my calculator has one button's log and right underneath it is the ln button. Sometimes you may have to use your second key to get to your ln, but they should be really close to each other on your calculator. Okay, the ln button works the same way as if we had the log, but instead of 10 being our base, this is when E starts to show up. Remember that number that we talked about the other day? So if E starts to show up, that's going to be that number that we can use to help us kind of use a natural log instead. So for example here, when the outside air temperature is anywhere between 72 degrees to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The function f of x equals 13.4 times ln x minus 11.6 models the temperature increase f of x in degrees Fahrenheit after x minutes, using the function to find the temperature increase to the nearest degree after 30 minutes. So where are we going to put 30 at in our equation? Yeah, it's going to go in for our x. We're going to do 13.4 times ln of 30 minus 11.6. Okay, so on your calculator, you're going to now go 13.4. You're going to hit your natural log button, the ln button, and put in 30 in the parentheses. Then we can do minus 11.6. And so let's round this to the nearest degree. How many degrees more would it feel like in the car? Yeah, it'd be 34 degrees more. Okay, so that means like if your car was somewhere in between 72 to 96, let's just say my car was 80 degrees, like if the outside temperature was 80 degrees, my car then would feel, if I increase 80 by 34 degrees, it would feel like 114 degrees in my car. That's what that equation is modeling. Okay, any questions on how to use the log or natural log button on your calculator?